So be there if you can. So let me start by saying something about the next homework, which is actually one of my favorite homeworks to talk about. This is kind of a neat homework. So here we go. What I want to do is I want you to kind of work through these problems. By the end of the section that we get to, by the end of this chapter, what I'm going to do is I'm actually going to give you very concrete ways to sort of compute Galois groups of polynomials. I'm going to show you some different techniques and stuff, but I think that this might sort of help kind of build to this, because here I ask you to kind of get your hands dirty doing some of this. So the first problem is consider the polynomial x to the fifth minus 3 in q of x. By the way, this polynomial is irreducible. Does anybody know why? What's that?
I was thinking Evans
It is.
criterion with p is equal to 3.
That is right. This is an Eisenstein polynomial with b to the 3. So this has to be irreducible. So take this, and of course, you all know what one root is, right? Cube or whatever it is, fifth root of 3, right? So let f be the field obtained by adjoining one of these complex roots, actually any one of them, it doesn't matter, and find the degree of f over q and show that this extension is not Galois. So if you just take one of the roots and throw it into q, see what you get, it's not Galois, as a matter of fact. Now, no, I have not had a stroke, because this polynomial is also important in finding all the roots. If you look carefully, this is the polynomial, this is the irreducible polynomial for a fifth root of unity. Show that this polynomial is irreducible over f. There's a couple ways you can do this, but one of the things you can do is use Eisenstein's criteria. Now, if you look at this polynomial, it doesn't look like an Eisenstein polynomial, but if you make a transformation to it, it becomes one. If f bar is the field obtained by adjoining all the roots of f of x cubed, find the Galois group of f bar over q. And I put this hint in here, and I'm going to explain this hint in a moment. This group must be a transitive subgroup of the S5. I'm going to come back to that in a moment. And then D, find an explicit formula for the 5 roots of f of x. Hopefully by radicals. You can actually find all 5 roots of this by using fifth roots, square roots, cube roots, things like this. And if you think about it, the way to do it. And then I give you another polynomial. Let's get old Jim off this picture, shall we?
So
yes.
When you say find an explicit formula, you don't want fifth root of 3 times omega to the 0, 1, 2, 3, 4, 5.
Yeah, see if you can give me something better than that if you can. So, but yeah, one of them should be the fifth root of 3, right? I consider that an explicit. See if you can do it by radicals, by square roots, or cube roots, or whatever. But you're right. You could do fifth root of 3 times those powers of omega if you just tell me what omega is. Number 2, consider the field f obtained by adjoining all the roots of the polynomial x to the 6 minus 3x cubed plus 1 to the rational number. So that should have 6 complex roots. Take them all and throw them into q, see what you get. Show that complex conjugation is a non-trivial automorphism of this field. Number B, if alpha is a real root of this polynomial, show that the map induced by taking alpha to alpha inverse gives rise to an automorphism of Q of alpha, where alpha is the said root. Show that the degree of F over Q is 12. It should be a 12 dimensional extension. Find the Galois group of F over Q. And again, find an explicit formula for the roots of f of x. Of course, and I'll make this remark here, the Galois group imparts And problems 2 and 3 must be transitive subgroups actually of F6, of F6. Number 3, consider the polynomial f of x is x to the 6 minus x cubed plus 1, and let f be the splitting field of f over q. What I mean by that is it's just the field obtained when you stick all the roots into q. Show that there is an intermediate field between q and f, such that the degree of E over Q is 2. So you've got an intermediate quadratic extension. Find the Galois group of F over Q and list all of the intermediate fields. And C, find an explicit formula for the roots. Notice the only difference between 2 and 3 is I just changed that coefficient and it changes things. Okay, any questions? Okay, I'm going to give you all, let me kind of give you a little primer to sort of help you down the road on this. I did make all these remarks about transitive subgroups, whatever that means. So before we move on to what we were talking about last time, let me give you kind of a quick primer on that. Consider Sn does anybody remember what it means for a subgroup of Sn to be a transitive subgroup? Remember what that is? Perhaps it might be, but it wasn't even defined last time, I'm unsure.
Related to back.
Yeah, so it's related to the action. So we say, let's say T in Sn is a transitive subgroup. Of Sn. If for all if for every element of the set, every I and j in between 1 and n, there exists sigma in T such that sigma I equals j. Right. So he's taking 2 elements, take any 2 things that you're permuting, there is some automorphism or some element of T that takes out of J. So let me give you an example. In S3, T is transitive. Right? Because take any pair, 1 and 2. Well, this one takes 1 to 2. You want to take 2 to 1, just do this one. You want to take 2 to 3, do this one. You want to take 3 to 2, do this one, and so forth. Right? In fact, it turns out that AN and SN are always transitive subgroups. For AN, we want N to be greater than 2. Right, because for N equals 2, AN is only the identity. If you look, it's not transitive. Because there's no way to take 1 to 3, right? You just can't do it, right? Example. In S4, E 1, 2, 3, 4, 1, 2, 3, 4. is not transitive. Can somebody tell me why?
There's no way to take 1 to 3.
For example, there's no way to take 1 to 3. However, this is kind of weird. Illustrates. Notice these two subgroups are actually isomorphic. They're both isomorphic to Z2 cross Z2. In fact, it might not even be clear that this is a fact subgroup, right? When you multiply this by this, but it turns out you can check that this is also isomorphic to Z2, and this one is transitive, right? You can take 1 to 2 and vice versa. You can take 1 to 3 and vice versa, 1 to 4 and vice versa, and so forth. Thanks. Yes.
So you say and vice versa. So you have the requirement that 4 goes to 1. So according to that.
Oh, yeah, you're right. I made a mistake here. How about that? Yeah. Yeah, I have to be able to make 1 to 2 and 2 to 1. I was sloppy when I wrote that down before. Okay, so let me kind of give you the primer. So this is kind of fun. Transitive subgroups. S2 is just S2. Right, that's it. Right. The identity in 1, 2, that's it. That's it. Transitive subgroups of S3 are S3 itself and A3. Which in this case is isomorphic to Z3. And that's just the group here, T. Transitive subgroups of S4. By the way, this list is up to isomorphism because there might be multiple copies of these in here. Anybody, okay, I'm gonna get the easy ones. There's actually 3 others.
Can you get the part in S4 that is that the copy of S3, and then you just need to add another transposition to take the.
Yeah, well, so once you've got an S3 in there, it tends to be the case if you add something else to it, then you'll get the whole. So the cyclic group of order 4. So the subgroup generated by the cycle 1, 2, 3, 4. Right, because the fact that it's got all those, to get anything to anything else, you just have to take an appropriate power. And so with that observation, anything that has a cyclic subgroup of order 4 should do the trick. So how about D4? Right, the dihedral group on the square. And there's one more. But not any of them, just the one that's isomorphic to this one that I listed. E 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And the transitive subgroups of S5 are S5, A5. And just like with S4, there's 3 others. Anybody want to guess? 2 of them you can rip off of the form. That's right, cyclic of order 5 and dihedral on the pentagon. And there's one more. I know what it is. I'll buy you back a popcorn. It's a little tricky. There's actually another subgroup of S5 that contains 5 cycle. It's called the Frobenius group 420. And it's generated by a 5 cycle and a 4 cycle. And I don't remember what the relations are, but if you ask me later, I'll figure it out. But it's generated by 1 5 cycle, 1 2 3 4 5. And then it's something like 2 3 4 5 or something. It's generated by 5 cycle, 4 cycles. It's got it's a subgroup of S5 or 20. And this is where I quit. Because up to isomorphism, there are 16 transitive subgroups. That's 6, right? Big mess. It turns out that F over K, well, let's say over Q is Galois, although you can extend this, and F of X is irreducible degree n. And F, the smallest field, so this is now friendly, containing. So let me erase this because I've got my statement written sort of funny. So suppose F over Q is an extension. I'm not going to say it's Galois yet. Suppose F of X and Q of X is irreducible degree n, and F is the smallest field containing all roots of F of X. So just like in the problem set that I told you, you take all the roots of this and throw it into Q. Then F is Galois over Q. There's no reason you should know this yet, but we will get to this soon enough. So that is, if you have an irreducible polynomial over some field, and it's a separable extension, which it'll always work over Q, and you throw all the roots into Q to make F, then it turns out that this field is Galois over Q, A. And B, the Galois group of F over, in this case, Q, is isomorphic to a transitive subgroup of Sn. Okay. So I think I've given you enough tools to explain why, if you believe that it's Galois, that second statement follows. Does anybody? Okay, can somebody explain to me why, assuming that when I throw all the roots in, that the Galois group has to be a, forget transitive, why does it have to be a subgroup of Sn? Yeah.
Like your name on possible.
That's right. Any automorphism corresponds to a fermentation of the hindrance. Okay, so that's where this business about subgroup of Sn comes from. Why does it have to be transitive? What is it about this transitive thing? This was a little bit trickier to see, but we've seen this before. Let's suppose U and V are roots of F bands. So these are two elements, of course, of F that are roots of the polynomial. Notice that Q adjoined with U is isomorphic to, correct. This is one of the things we learned, that taking this field and adjoining one of Bruce's polynomial, this is isomorphic to polynomials over the field modded out by its irreducible polynomial. This gives it a degree n extension, which might not be all of that, but it's a subfield of that. And of course, there's no difference between U and V. This is isomorphic to Q and V, right? Because they're both roots, right? This is isomorphic to this. I can't tell U and V apart. This is isomorphic to this because it's another root of this. And so there's an isomorphism from here to here. And with what we're talking about now, we know that this actually extends to an isomorphism from F, or I'm sorry, an automorphism from F to F, because these are both subfields of F. And so we have an element of the Galois group, an automorphism of F, that takes U to V. That's where the transitivity comes from. Given any pair of unit roots, U and V, and there's n of them, there has to be something in the Galois group that takes U to V, and that's why it has to be transitive. So that gives you an idea. We're gonna fill in some of these blanks presently. Any questions so far? Okay, so let's pick up where we left off last time. So lemma 8.2.15. If F is Galois over K, and E is a stable intermediate extension, and recall that this means that sigma of E is contained in E for all sigma in the Galois group. It doesn't necessarily fix E, but everything in E stays in E. Then E is Galois over K. Okay, so let's go through the proof of this. Okay, what we're trying to do is we're trying to show that E is Galois over K. That means that E, that the fixed field of the Galois group of E over K must be exactly K. Hopefully y'all remember this. Let U be in E, but not K. Right? Part of our burden is we have to show, all we have to do to show that E is Galois over K is to find an element of the Galois group of E over K that moves this, right? That was, remember how equivalent to saying that the fixed field of the Galois group of E over K is K. This is equivalent to saying that if you have any element of E that's not in K, I can find some automorphism of E that moves it, right? So let U be an E minus K, in particular, U is not a K. So there exists sigma in the Galois group of F over K, such that sigma of U is not equal to U. Right? Because this is our assumption that F is Galois over K. Can somebody tell me how this finishes things for me?
That just means that forces into be in Galois F over K. like the things prime, which needs to be in the one, so they will be equal.
Okay, so now consider the sigma restricted to E. Sigma restricted to E goes from E to E, since E stable. Right, because we know that you go into E here. So in particular, of course, we can restrict any element of the Galois group to E, but that doesn't necessarily mean that this goes into E. It might go flying off into some other subfield. But here, because it's stable, we've got that going for us. And so notice that E is in Galois group. P over K. Right, because it's an automorphism of E that fixes K, and sigma restricted to E of U is not equal to U. So E is Galois over K. Okay. Here's another lemma to throw in. Any questions? Questions? Here's another one to throw in the mix, and you'll see where this is kind of a companion to the previous one. But A, B, F, B fields. And suppose that E is algebraic in Galois. Okay. Then E is stable. And this one, the proof actually is going to give us some insights for later. So this proof is kind of important. Maybe not so much directly for this result, but just it illustrates things that are going to be important to us. So here we have a tower of fields. Notice that we've got kind of loosened assumptions because if E is algebraic and Galois over K, then E is stable, right? Usually we were assuming that everything was all finite, everything's algebraic, but we're loosening things a little bit. So we need to show that E is stable. So we need to show that for any element of the Galois group of F over K, any automorphism of F, it has to push stuff in E to something else in E. So let's let U be in E and let F be the minimal irreducible polynomial. Irreducible polynomial U over K. Of course, since E is algebraic over K, such a polynomial exists. So let's see, I'm gonna do this up to R. So let's list the distinct roots of F of X that lie in E. So let's look at this polynomial. It's got some roots. It's got at least one. Of course, U must be a root of this polynomial, just by the way we built it. And maybe there's more. So I'm gonna let these be the roots. U1 up to UR. And let me point out, of course, that R is less than or equal to N, which is the degree of f of x. So if we say that the degree of f of x is N, the number of distinct roots must be R, which is bounded above by the degree of the polynomial. So let this guy be in the Galois group of E over K. Then permutes the roots. U1, U2, UR right, it must permute every automorphism induces a permutation of these distinct roots. So check this out. And this is kind of where the observation is kind of cool. Okay, I'm just gonna build this, I'm gonna get out my Legos and I'm gonna build this polynomial, right? For every one of these distinct roots, I tell you, so this polynomial will be of degree R. If there's an x minus ui for everyone, I just multiply this. Can anybody make an observation about this polynomial? What happens when I apply so I'm being a little bit loose. What do I mean by applying an automorphism? It's supposed to be an automorphism of E to G of X. What I mean is apply this automorphism and leave X alone. I'm just messing with coefficients. It stays the same because no matter what tornado is here, it induces a permutation of these distinct roots. So all it does is maybe it takes U1 to U2 and U2 to UR and all it does is just really permute these factors here and you get the same outcome, right? So G of X is fixed by all so the coefficients of G of X lie in fixed field of right, because we're assuming that E is Galois over K. So the fixed field of set of automorphisms is K. The coefficients must be in there. This is an incredibly important observation, which is. This is sort of like, we've proved something even more important to prove our lemma. What does this tell me? Notice that notice the g of x must divide f of x, right? Because f of x is some nth degree polynomial, right? G of x is just some subproduct of this, right? Because what happens is f of x has all these roots, distinct roots, and maybe some more stuff, maybe some powers. So this stripped down version is g of x must divide f of x, right? But f of x is irreducible. Because this was the minimal irreducible polynomial. So well, let me be careful here. G of x equals f of x if f of x is monic, which we can certainly assume here, right? So the minimal polynomial for f of x or for u must have all distinct roots. This is an incredibly important observation that in this Galois case, that the minimal polynomial for u must actually have all distinct roots, and they are all in E. Right? Because remember, these roots are the distinct roots that lie in E, and this thing actually turned out was f of x. So in this situation where E is algebraic Galois, any element in E that's not in K has this irreducible polynomial that has distinct roots all in E. Therefore, so here's kind of the anticlimactic end to our proof here. This means that sigma of u is in E and E is statement. But I think that really these few lines right here of observation are far more important. We know that u actually has its minimal polynomial, has distinct roots, and all the roots must lie in E. Okay, any questions on this?
So we got distinct roots because we constructed G with distinct roots and found that G is equal to F.
That's exactly right, right. You almost feel like you kind of got away with something there a little bit. So here is, I think, the final tool, and then I'm gonna do this kind of final tool which ties almost everything up, and then I'm going to give you another statement of the fundamental theorem of Galois theory that's perhaps a little bit more general. So this should take care of things in the situation that we claimed, and then I won't generalize a little bit. A217. What Kn EBF feels. With B stable. Then the Galois group modulo of the Galois group of F over E. Is isomorphic to the Galois group of E. Actually, I got carried away. Stated this way is isomorphic to the automorphisms of E, fixing K of course, that are extendable to F. So these are actually the ones that we can extend to F. Proof. So we define map F from the Galois group F of K to the Galois group of E over K. As follows. So my input is an automorphism of F that fixes K. My output is going to be an automorphism that fixes K. So I'll just restrict this down to E. The image of this is the subgroup of automorphisms that are extendable to F. So if we say consistent of automorphisms. Then and that should be fairly obvious because after all, in the end, every one of these things in the image comes from an automorphism of F, and that's why they're extendable. Notice that if you look at the kernel of this map, this is sigma, such that sigma restricted to E is equal to the identity. So we want sigma restricted to E to be the identity on E. So this is the Galois group F over E. That is the automorphisms that fix E. And so now just apply first isomorphism theorem. Now, let me make a remark or two about how this finishes things up for us. Yeah. If E is an intermediate extension that is Galois over K, and E is Galois over K, then. And remember the condition we have. So E prime. Which is, then E prime, must be normal in Galois. Okay, right. That's what we needed. We showed earlier that this is what we needed for E to be Galois. Since E and E prime are closed. Since these extensions are closed. And G prime equals K. As G Galois. As F is Galois. Over K, where the so that's what I'm going to G. Then the order of G mod E prime which is the index of E prime and G, is equal to E double prime for the index of, or I'm sorry, the degree of the extension E double prime over G prime, which is E over K. Because remember, E is closed and G prime is equal to K. And so what we've shown effectively is G mod E prime Galois group of F over K mod Galois group of F over E this is actually isomorphic to a subgroup of the Galois group of E over K. Of order precisely equal to the index of, not index, the degree of the extension E over K. And that's all we need because now we have G mod E is isomorphic to Galois. Okay. And that's the last thing we had to sort through. Now, let me give you this more general statement, and that'll be that for spring break. So this will be the final statement. I'll leave this unproven. It's a little bit more general than what we have, what we proved earlier, but let F be a field and G a group of automorphisms in F. And G a group of automorphisms of F. And K the fixed field of G and F. So you don't, so all you have to do to identify what it's Galois over is just look at that group of automorphisms and take the fixed field. Then F is Galois over K. Over K, and if G is finite, then F is a finite dimensional Galois extension of K. Extension K with Galois group. So that'll finish off this part of the fun. We'll finish off the fundamental theorem, Galois theory. We're going to talk more about some subtleties, separability, how this other stuff comes up, and actually some practical stuff on how to compute this. Any questions? Well, I hope you all have a fabulous spring break. Think about coming by the math club because no spring break is complete without having a math club first. Other than that, you all have a good break and we will see you on Monday next.